Well, hopefully you recall that simple machines afford their users the opportunity to do work using a small effort force, or in other words, somebody who's not very powerful can get a task done in a simpler way. But don't make the mistake of thinking that simple machines reduce the amount of work that has to be done. So for example, let's say you have to lift some really large, heavy box or trunk up into the rafters of your garage. So one option would be brute force. Just get down below the trunk and lift it straight up. You'd have to be powerful to do so if the trunk is heavy enough, and you'd have to exert a large effort force. So the alternative is to use a pulley system. And in this example, we're told that the pulley system has 4 lifting strands. So it probably looks something like this. There's probably a double compound pulley at the top, and then attached to the trunk is another double compound pulley. So you take a piece of rope, wrap it around the top pulley, and that goes down below the bottom pulley, wraps back up to the other pulley on top, comes back down and wraps through the second bottom pulley, ultimately comes back off and then anchors off to the top pulley combination. So we just need to connect that bottom combination somehow to our trunk, and then if you apply a lifting force by pulling in this direction, we'd say that's your effort force. And you can see, because there are 1, 2, 3, 4 pieces of rope that are going to get shorter as this one gets longer, then there must be what we call an ideal mechanical advantage of what we say 4 to 1, or it's just as well just to say the ideal mechanical advantage is 4. So we're told in this problem that the trunk has a mass of 60 kilograms. If we let G equal 10, then we can say that the weight of the trunk is 600 newtons. So our first question asks, if the machine is ideal, how much applied force would you have to give? Well, certainly less than 600 newtons. You can probably do the mental math on this one and realize the answer is 150 newtons. But to be clear, efficiency can be calculated as the AMA divided by the IMA. But if the efficiency is 100%, then that means the AMA is equal to the IMA. And the AMA is equal to the ratio of forces. It's how large your effort force is compared to the resistive force that you're trying to overcome. Actually, I've written that in reverse, haven't I? It's the resistive force divided by your smaller effort force. This means that the effort force is equal to the resistive force divided by the AMA. So in this case, it's 600 newtons divided by 4. Yeah, of course, 150 newtons. And that's the benefit. You'd probably much rather only have to exert a force of 150 newtons than 600 newtons. The next question asks, if the rafters are 3 meters high, how much rope passes through your hands? So if you have to lift this box a height of 3 meters, do you pull 3 meters of rope through your hand? No, of course not. This one segment of rope is getting longer while 4 other segments are getting shorter. So to say that the IMA is equal to 4 is really a way of saying that the ratio of the effort distance divided by the resistive distance, or in this case, the effort distance divided by the height, is equal to 4. And so the effort distance is 4 times the height, so 12 meters in this case. So let's write these correct answers up here to keep track of everything. Next question. If the person actually exerts a force of 175 newtons, not the ideal case of 150, then what's the AMA and what's the efficiency? Okay, so in the best case, the least possible amount of force you could apply to lift a 600 Newton object with a pulley with 4 lifting strands would be 1/4 that value, 150 newtons. But see, we're not taking into account that these pulleys actually weigh something. And so that adds to the effort you would have to use that you wouldn't otherwise have to lift if you just directly tried to lift the trunk with the brute force method. Also, these pulleys might not be well lubricated. They might be a little rusty or squeaky, and so that adds some extra resistive forces. So 175 newtons is still better than 600 newtons. It still makes it easier to do, but it's just not the ideal case. So what would the AMA be in that case? Well, AMA is always a ratio of force. So it's the resistive force divided by the effort force. So it's 600 newtons divided by the actual case of 175 newtons. If you grab a calculator, when you divide 600 by 175, you get an AMA of 3.43, and notice that's less than the ideal mechanical advantage. In fact, the efficiency can be found by taking a ratio of the mechanical advantages. If we divide the AMA by the IMA, then 3.43 divided by 4 gives us a value of roughly 86%. And lastly, what's the work input and what's the work output? The work you put in is your effort force, in this case 175 newtons, multiplied by the effort distance, which in this case is 12 meters. The work you get out is the resistive force you're overcoming multiplied by the distance that moves through, or in this case, it's just as well to call it h, the height of 3 meters. So this is 600 newtons times 3 meters. So we can do this one in our heads. This is 1,800 newton meters. 1,800 joules is the result of your effort, but the effort you actually had to put in is 175 times 12, which is 2,100 joules. So notice, the use of the simple machine requires you to do more work than you would otherwise do using the brute force method. So why in the world would you ever use the pulley system? Why use the simple machine? Well, because even though you end up doing more work, you were able to do it with a much smaller force. 175 newtons is much easier than 600 newtons. So there's a cost, but in most cases, it's worth it unless you're using a really rusty or really heavy pulley system. And just to double check that we got this right, the other way we could have calculated the efficiency is to divide the amount of work we're getting out by the amount of work we have to put in. So if we do 1,800 joules divided by 2,100, that better come out to 86%. Let's see. Of course. Thanks for watching.